Hi, everyone. It's great to see people coming and joining us. We will start the webinar in about a minute. We will just wait a little bit more for everyone to join. So let's give it like 30 seconds more as we see more people popping up. So let's start the CLT Shear wall design for mass timber office buildings webinar. My name is Milica Grmusha, and I am a part of the marketing team of Spectoolbox. With us today, we have Filip Cirovic that will be presenting the webinar, and then we have Marko Dimitrijevic joining us as well. So to start us off, I'm going to tell you a little bit about Filip first. He's a technical development representative and has several years of experience in mass timber design. He started the mass timber design adventure since his master thesis. He did the master thesis on the topic of the design of CLT buildings with an emphasis on seismic design. And since that, he's been working with Spectoolbox since December 2024. So soon he will be telling us more about the CLT shear wall design. Let's start with Spectoolbox as well. So for everyone who is new to Spectoolbox, it's really great to meet you and it's really great to see you. Our mission is to make innovation easy to specify. We are a team of 55 software and structural engineers, and we are very proud to say that we are a very global company in a way. So we are based in Indonesia, in Ethiopia, in Australia, and in Serbia. That's where our teams are based. We started this adventure in Australia in 2023, and now our software is being used pretty much all over the world. So we have different regions for Australia, New Zealand, Europe, and UK, and then North America. And what we do is we build software for the design of mass timber, EWP, and connection products. Our supplier partnerships, the global network is really growing since 2023. And you can see it here that we are working, and we are very proud to be working with some of the great names and great companies from the mass timber industry. And this is just the start, let's say. So this is already a great network, but we are getting new suppliers and new partners pretty much each month. And this network is really growing quite fast. To jump into the agenda for today. So after the Spectoolbox intro, I will pass it on to Marko to tell us about the latest update that are coming to the app. Then Filip is going to tell us, he's going to lead us through the CLT shear wall design webinar. And at the end, we are going to have a Q&A time for the Q&A, so for all of the questions. And the way that we do it is you can use the question icon on the bottom of the screen, where you can write down the questions throughout the whole webinar. So if any questions pop up at any moment, you can just write them down. Feel free to introduce yourself at any point, or just write general comments in the chat function. So you have both chat function and then ask questions in the Q&A section. That's it from me. I'm gonna pass it on to Marko to lead us through to take us through the updates in the app.
Thank you, Milica, and hello, everyone. Really nice to see you today, and welcome to our new episode of CLT Shear Wall webinar. So I'll briefly take you through some of the updates today, and after that, I'll just reset my screen. Apologies. Yeah, and right after that, I'll pass on to Philip, so he will take you through the details of CLT shear wall theory and a practical example in the app. So really quickly, I'll just mention about our progress in the last few months. So we released a char module globally. So this is something is a big improvement to the current CLT fire, but also on timber members as well. We also improved panel-to-panel connection details, and we have new database structure and improves visualization across the app. What's ahead of us is, of course, CLT shear wall that we'll present today, but then hanger modules, new UX, new UI, and also we'll leaning into the direction of new categories, including acoustics, pacifier envelopes, and sustainability. In terms of next milestones that we'll reaching, so you can see here a near-term roadmap that includes some of the releases that are scheduled, but also some things that we are working on the back. So as mentioned, so if you haven't checked already, you also have this new releases already in the app. So fire module, as I mentioned, is improved to the latest Eurocode from 2025, but also with the new functionality, you can access fire design directly through add fire button within the regular or ambient design. Also, panel-to-panel connections, new version is available in the app. So 3 connection details, including half lap, spline, and butt joint, are improved to new version. So covering latest Eurocode, suppliers ETA, and some of the improvements along other functionalities and visualization. In terms of the upcoming updates in more detail, so shear wall design is something that Philip will take you through in detail very shortly. Hanger modules is something that we are finalizing and something that you can expect in the coming months. So practically with major suppliers that we are working with, we developed a completely new category module with some of the most popular products that are being used in the industry. Also, we are lifting the whole app with a new visualization. So just a preview of in what direction we're going and how a user will be able to navigate to both inputs and outputs. Well, and at the end, before I pass to Philip, just want to mention that anyone who's interested or first time with us in checking the app in more detail, we are offering also 30 days of free pro trial. So just leave us your email or reach to us or the website or through our emails, and we'll happily to provide you full access to the app. So then being said, I'm passing on to Philip, and yeah, looking forward to any questions or your comments at the end. Thank you.
Hello all, welcome to the webinar. So I'm not going to introduce myself because Milica already did a great job, so I'm not going to waste time on that. And just let's jump into the webinar for now. Screen. So in this episode, we will cover CLT shear wall design using European design codes and talk about design methods, in-plane shear strength, and showing the steps needed to calculate the seismic lateral force. Then we will check the freshly updated CLT shear wall calculator and show how it can be used to design a multi-story shear wall. So at the beginning of this webinar, let's take a look at the shear wall's importance and available methods for the member design and its connections. CLT is gaining popularity mostly due to its excellent resistance to both in-plane and out-of-plane loadings, making it one of the key components in lateral load resisting systems. A lateral load resisting system is designed to manage lateral forces that could arise from wind and earthquake. And this system includes shear walls, frames, floor and roof diaphragms. Shear walls play a vital role by transferring the lateral forces from the diaphragms to the foundation or supporting systems. So in order to design a CLT shear wall, we need to assess its load carrying capacity and stiffness. The analytical methods used for designing CLT shear walls are based on the 4 different contributions of the shear wall deformation. So that is panel bending deformation, panel shear deformation, translation deformation, or it's slip, or rotation deformation, rocking. For most shear wall configurations, the contribution of the in-plane shear and bending deformation are much smaller than the deformations from translation and rocking, which is governed by steel connections that typically exhibit a much softer behavior. That is why the majority of these analytical methods consider the wall panel as rigid, so i.e. the deformation of the CLT panel itself is disregarded in favor of the connections. So here we will show the different methods for determining the lateral load carrying capacity of CLT shear walls that are available on Spectoolbox's shear wall calculator. So the first one is, the first method is by Casagrande. It is a simplified analytical method which analyzes shear walls using rigid body rotation and static equilibrium with the rotation point at the panel edge. The second method is by Wallner-Novak. It uses a simplified rectangular stress block, which is 25% of the wall length, and accounts for frictional resistance. And the third one was developed by Tomasi, who proposed a stress block method where the non-linear stress distribution for wood in the compression zone is substituted by a rectangular stress block with a length based on the compression strength of the CLT. Now, the fourth method is by Pei, which considers the CLT panel as a rigid body rotating around one of its corners with each angle bracket resisting overturning, as we can see here in this image. It should be noted that the proposed method does not explicitly consider the sliding resistance of the shear wall. So the angle brackets are assumed to be only taking in the tensile forces. The fifth method it was developed by Reynolds and enhances the triangular tensile distribution method by including a compression zone and factoring in friction to improve sliding resistance evaluation. And the final sixth method is included in the latest update to the shear wall calculator. The method is by Gavric and Popovsky, and it considers interaction of shear and tension forces, specifically in the angle brackets, as tests show that hold downs do not provide any significant resistance in the shear direction. So after presenting all these methods, you may wonder which is the correct method to use. It depends on the design scenario. So Casagrande's method was developed for a single-story shear wall. The Gavric and Popovsky method can be used when angle brackets with a significant tensile strength are spec'd out. And for a seismic design, the 2022 version of Eurocode 8 specifies that the Tomasi method should be used. So the next integral aspect of the strength of CLT shear walls is the in-plane shear strength of CLT. So in solid materials, shear stresses resulting from transversal forces can be assumed to be constant over the element thickness. In CLT panels, where adjacent lamella within individual layers are not glued to each other at their edges, however, the thickness is not constant throughout the beam. So that is for the non-edge glued CLT, which is like the most common scenario for CLT panels. So in sections that coincide with the unglued joints between neighbored lamella, shear forces can only hence be transferred by lamella arranged perpendicular to that joint. The shear stresses in these net cross sections will consequently be greater than in the gross sections in between unglued joints. The transfer of shear forces between longitudinal and transversal layers also causes shear stresses in the crossing areas of orthogonally bonded lamella. Considering both shear stresses in the lamella and the crossing areas, 3 different failure modes can be distinguished in the CLT panels subject to shear stresses. So here we will show the three different in-plane shear failure modes as presented by Wallner Novak. Failure mode 1 is characterized by shear failure perpendicular to the grain in the net cross-section of a panel. The failure occurs in sections coinciding with unglued joints with shear stresses only in the lamella perpendicular to the joints. So that is the net shear failure. And we can see here we need to use AS net, so which is the minimum of A0 net or A90 net. Failure mode 2 is characterized by shear failure within the crossing areas between orthogonally bonded lamella. So that is the glued surfaces between the layers. The failure is caused by torsional and unidirectional shear stresses resulting from the transfer of shear forces between adjacent layers. And failure mode 3 is characterized by shear failure parallel to the grain in the cross-section of the element. The failure occurs in sections between unglued joints with equal shear stresses in longitudinal layers and transversal layers. So for today's example, we have a 4-story mass timber office building with an L-shaped base. In the next few slides, I will quickly go over the steps needed to design a multi-story CLT shear wall for a seismic load. But first, to just quickly go over the building specifics and preliminary design results. The project is a 4-story office building, as I said, with overall dimensions of 15 by 20 meters, story height of 4 meters with a total height of 16 meters. The floors are made from single, 2-span, and 3-span CLT slabs spanning in both X and Y directions. The slabs themselves are supported by glulam beams and CLT walls. And for vertical support elements, we have glulam columns and CLT walls, while the lateral load supporting system is a series of CLT shear walls. So first things first, we need to set a structure of the building by performing a preliminary gravitational load design. So we start off with determining all the dead, live, and snow loads, if we have any snow loads. Then we set the positions of all the structural elements. Next, we calculate the UDL acting on each wall at each floor, which is also needed to calculate the lateral load capacity of the shear walls. Finally, we design all the floors, beams, columns, and walls for those gravitational loads. So based on the preliminary design, we have already designed floors, beams, and columns. So here we can see for floors, we use KLH's 140 millimeter panels with 5 layers. For walls, it is the KLH 130 millimeter panel with 5 layers. For beams, we have 200 by 580 GL24C. For columns, we have 260 by 260 GL28H. So, a second. So now we will try to go over the key steps in determining the seismic forces acting on each shear wall at each shear floor. The first step is to pick the number and the type of connectors for each shear wall at every wall-to-floor joint. Then the next step is to calculate the sliding and rocking stiffness of each wall-to-floor joint. This can be done following the provisions in the Annex H of the new Eurocode 5, which use the stiffness of the hold-downs and angle brackets. And here we can see the formula. So the first one is the rotational stiffness of the joint. The second one is the sliding resistance. And we can see from this image, so this first parameter is the stiffness of the hold-down, or angle brackets also, if we have angle brackets that can transfer the tensile forces. And this parameter here is the slip of the angle brackets in the shear direction. So following that, we need to calculate the horizontal stiffness of the complete multi-story shear wall. This can be done again by following the Annex H. In Annex H, so we have how to just hide this. So in the Annex H, we have formulas how to calculate the story drifts, and story drifts have 5 different deflection components. So we have panel bending deformation, shear panel deformation, rocking due to elongation of the hold down, rigid body sliding, and a rotation of the top of the shear wall panel underneath the panel that we are designing. So we can see here that is the angle of rotation at the bottom here. So to calculate the stiffness, we will need to sum up all of the deflections, or rather the storey drifts. And as we can see here, summing them all up, we have the deflection at the top of the shear wall. And at the end of the webinar, I will show how to use Spectoolbox to calculate these stiffnesses. So the calculation from both of these points will be added in a further update to the CLT shear wall calculator, as we are continuously working on adding functionality to our calculators. Although not according to the latest version of the Eurocode, Spectoolbox uses a deflection calculation presented by Walden Novak, which can be also used to assess the stiffness of the complete shear wall stack. So after we have all the wall and connection stiffnesses calculated, we have to calculate the fundamental periods using FEM by modeling the shear walls as 1D elements with calculated rotational and translational stiffnesses entered as nodal springs or releases at each floor. So at this point, you may wonder if we need to use FEM for the dynamic analysis. Why not just design the shear walls using FEM? For that, we have a couple of reasons. The first is that the previously presented methods are experimentally verified, and the new Eurocode 8 states that the Tomasi method should be used for determining the strength of the shear wall. Another reason is that to accurately replicate the behavior of a rocking CLT shear wall, the engineer would have to enter very specific nonlinear support conditions at the joints of each shear wall panel. So tensile forces could be only transferred through a single node, which would represent the hold down, and then the rest of the wall to floor joint would have to transfer only compression forces and shear forces. So this will make the process of modeling the structure very tedious, and also the subsequent calculations by the software would be too time consuming. So after we have our fundamental periods, we need to determine the building consequence class, soil class, limit state, peak ground acceleration, seismic response spectrum, and all the necessary parameters. After that, we determine the behavior Q factor based on the ductility class. And then finally, we calculate we calculate the base seismic shear based on the mass of the building and seismic response spectrum. Next, we have to calculate, so we have the base shear, the complete seismic base shear. So next, we have to calculate the seismic forces acting on each floor based on the mass and displacement of each floor under acceleration of gravity. Then we need to calculate the center of stiffness and center of mass. To determine the center of stiffness, we will use the previously calculated stiffnesses of the shear walls and their position. The final step is determining the seismic shear forces acting on each wall at each floor by using the wall stiffnesses, eccentricity between the center of mass and center of stiffness, and the position of shear walls relative to the center of stiffness. So going further, we will now take a look at the CLT shear wall design. In this example, we will share with you the updated CLT shear wall calculator, which will be released shortly on the app. So for now, let's assume that I have done all of the previous points that I've explained, and we have designed our structure, and we have some in-plane shear forces from the earthquake. So first, we determine the dead loads on the wall from the CLT slab at each floor. So here is my CLT. Here's my shear wall that I will design. I have shaded here the tributary width. So the tributary width is 5 meters. Roof dead load is 1.5 kilonewtons per square meter. Floor dead load is 2 kilonewtons per square meter. And here I have summed up all of the dead UDLs acting on that floor at each floor. And here we have the shear wall in question. So these are the in-plane shear forces that have been calculated earlier. So designing this complete shear wall stack using Spectoolbox, we need to go panel by panel or floor by floor. So first we have top floor. We have a vertical dead load of 7.5 kilonewtons per meter. In-plane shear force of 25 kilonewtons. And for the connectors, we use Rotablasis TTN 240 angle brackets. And for the hold downs, Rotobus is WHT 30 hold downs. So now I will show this on the app. So here at the beginning of our calculator, you can select the region, units, Europe in metric, of course. Then after that, we have the print PDF report and the save button. So now the first inputs we have, as I said, so CLT layup, CLT supply is KLH, 130 millimeters, 5 layers. And here we have our dynamic image of the CLT shear wall. So you can see here the in-plane forces, the UDL, the brackets, and you can also look at it in many different projections. Just gonna leave it like this. So then we go to the inputs. So we have the geometric data. Outer lamellas are always primary vertical because that's the strongest directions for a shear wall. Then we have the longitudinal and transverse lamella widths. So here I have just entered 150 millimeters for both. And these lamella widths are important for determining the in-plane shear strength of the CLT panel. Height of the panel is 4 meters, panel length 3, edge distance here, so that is the edge distance of the hold downs, and I have entered the as 200 millimeters, so you can see here, so that is this edge distance here. So, and then we have the tensile wall strip width. So this is a manual input that we have to make it easier to have the engineers have more control over determining the tension capacity of the panel itself. So you can determine, so in the hold down area, we have tensile stresses. So we let the users determine themselves the width from through which that tensile stress is transferred. I have entered here 0.5, half a meter width. Then after that, we have the design methodologies input. So design code, Eurocode, in-plane shear method. So that ProHoltz, that is the Voller-Novak method that I explained earlier. We also have FP Innovations that was developed in Canada, but it basically describes the same 3 in-plane shear failure modes that I have described earlier. So, and then we have the input for the wall connection methods. So those are the 6 connection methods that I've talked about. So because this is a seismic design, the new Eurocode 8 states that we have to use the Tomasi method. So I have selected the method 3. We have here the wall floor interface. So this is timber to timber. And this is very important for this method in particular because it determines which compressive strength is used to calculate the length of the compressive zone. So if I specified timber concrete, that means that the wall is supported by a concrete foundation. And then for determining the length of that compressive zone, we would use the compressive strength parallel to the grain of the CLT wall panel. But when it is timber to timber, we use the compression perpendicular to the grain strength of the CLT floor. Now we have the design constants input. So because it's seismic design, I have entered the gamma factors as 1, K mod as 1.1, which is for the instantaneous load. System factor, I have left it as 1. And KC90, it's, as I said, so it is used for determining the length of the compression zone. And here I have entered just 1 just to get the most conservative result. Pre-drilling, no, that is for the brackets. And then we have underneath here, missing material properties. So these are the 3 in-plane shear strengths for the 3 in-plane failure modes. And here I have entered the recommended values that are presented in the new Eurocode 5. So for the gross in-plane shear strength, it is 5 megapascals. For the net in-plane shear strength, it's 5.5. And for the torsional strength, or the strength of the glued surfaces, it is 2.5. Then we have connector data input. So here we select our suppliers. So I have selected Rotobus. we can select on if we want the connectors on one side or both sides of the CLT wall. Number of hold downs is 2, and here we can also determine the number of angle brackets. So I've entered here 6. So here, as I said, angle brackets are TTN 240, hold down WHD 30, and beneath both of them, you can select which fasteners are used for this type of connector. And I've just selected the LPL nails. And just go to the next one. So loading data. So because it is top of the shear wall, the bending moment is 0. The in-plane shear force is 25, and the gravity load is 7.5. And then we have the deflection data input. So here you can enter the lateral deformation limit of the CLT shear wall. Then I have entered here a calculated allowable storey drift of 15 millimeters. So then we go to the results. So first we have the output summary, where you can see if everything's green, if everything's working fine. So it seems to be working in order. And after that, we have just the summary of the results. Then we have the detailed results. So we have the first tab is the properties tab. Here we have the thicknesses of the layers, the grades, modulus of elasticity, and various strengths. And here we have the calculated in-plane bending stiffness. So the next tab is the connection modeling. So here we can see how the compressive and tensile forces are calculated using the selected connection method. So here is that Tomasi method that I have described. And here you can see, because it is timber to timber, it uses the compression resistance perpendicular to the grain, and it uses the complete width of the complete thickness of the CLT wall to determine the length of the compression width. So here we see that the compressive zone is 160 millimeters. And next tab we have the lateral deformation. So as I said, Spectoolbox uses a Wallner-Novak method, and it's very similar to the new Eurocode 5 version, but of course we will also have that the deflection according to Eurocode 5 added also. But just to quickly go over it, so we have the bending deformation of the shear wall, we have the shear deformation of the shear wall, we have expansion of the tie rod, so the rocking the deformation, and we have the slip, or rather the sliding, the rigid body sliding of the CLT wall panel. So as you can see, the only deformation component or a deflection component that we don't have that the new Eurocode 5 has is the rotation of the top of the shear wall underneath the panel we are designing. And so here we have the overall deformation of our wall summed up. So the next we have member design tab. So here we have normal stress verification, shear stress verification, and buckling. So for the normal stress verification, we are checking the tensile strength, and this check uses that tension strip with input that I have described earlier. And just we can see here that it is 2.9%, so utilization is correct. So we have nothing to worry about there. Then we have the shear stress verification, and here we have the checking of those 3 different failure modes that I described. Very detailed calculations, as you can see. And then after the shear stress verification, we have buckling. So buckling here, even though our compressive zone is 160 millimeters, we are checking the buckling for 1 meter strip. But usually buckling rarely occurs in CLT shear walls. From all the different testings, we know that the most common failures of CLT shear walls are the connections themselves. But still, we have added this buckling check. And then at the end, of course, we have the connection design, or the connector design rather. So we have hold down capacity is calculated, and it is using the ETAs of Rotoblast to calculate this. I can see in here, we see the hold down capacity with a utilization of 46%, so we're good to go. Then after that, we have the hold down stiffness calculations, and here we can see it is 26.1. And then angle brackets, so basically the same stuff. So calculating the strengths using the supplier ETA, utilization, calculating the stiffness of the angle bracket, which is used for determining the sliding deflection of the shear wall. So basically that is our top floor panel of the CLT shear wall. So let me just go back to the presentation. So how you would design this whole shear wall, you would go floor by floor, going through all of these different inputs and outputs. But for the sake of time, we will not go through each floor. We'll just jump into the bottom floor, the ground floor. So we have a vertical dead load of 23 kilonewtons per meter, in-plane shear force 62 kilonewtons, in-plane bending moment 492. We have the angle brackets that we use are Eurotech HB shear angles, and the hold downs are Eurotech tension rods 440. So now we have this. So I'm not going to go over all of the inputs again. I'm just going to show this. So the design, so because it's a ground floor, it is supported by the foundation. So here I have entered the timber concrete as the interface, and I have left the wall connection models for method 3. And here we can see, I'm just going to jump into the connection modeling, and here you can see the compression with it. So the compression that is used is the compression resistance parallel to the grain, and with the thickness that is used is the thickness of just the vertical lamellas in the wall panel. And here we can see that even though the loading is much higher, because we are using much higher compression strength, the compression width is almost the same as for the top floor. For the top floor, it was 160 millimeters, and for this one, it's 170. And so here we have the calculated tension and compression. So as we can see here, the tension is pretty high, 227 kilonewtons. So we will check the connection design. So most likely we are failing the hold down check. Yeah, as we can see here, it is 398%. So let's maybe try to check to change the connector for the hold down. So I know Eurotech has one hold down that has pretty high strength. So that is the hold down high load. We're going to check what happens now. Okay, so we are at 164% utilization, a lot better, but we are still failing. So what we can do now, we can, because this the shear wall is not on the facade, it's inside of the building, so we can place our connectors on both sides of the wall. So we can select here both sides, and then of course it's going to be halved, so 82% hold down. And I think when we go to the output summary, everything else is fine. So our CLT shear wall is good to go. But I'm just going to go over one additional thing. So let's imagine that perhaps our loading is not seismic loading, it's wind loading. So we don't have to use this Tomasi method. We can maybe select the new method that we have. So because the HB shear angles also have high tensile strength, I've selected the new method, which takes into account the tensile and shear forces acting in the angle brackets. So here we can see how that is calculated. And as you can see here, the tension of the hold down is quite smaller, but then we have the tension on the angle bracket, which is a different problem that we have, but let's check what is happening. So I'm going to go in the output summary. So angle bracket is at 93.6, fine, but the hold down is at 20%. So we can maybe use a lighter tension rod. So let's go with maybe 340. So yeah, here we have 55% and then 93%. So we saved a little bit. So we are using hold down that doesn't have such a high strength. And so, but as I said, so because this is a seismic design, I'm just gonna go revert back to the method 3. And so that is the algorithm for the designing the CLT shear walls using Spectoolbox. And I just want to go through one more thing on the slides. So as I said before, you can use the Spectoolbox's current calculations for determining both the connection stiffnesses at wall-to-floor joints and the complete horizontal stiffness of the complete shear wall stack. So for the connection stiffnesses, we have this formula from the New York 05. And as you can see here, so this first parameter, that's the stiffness of the hold down. This here is the compression width, or rather the length of the compressive zone. So you can see here. And here I have calculated for our wall, for rather all the floors above the ground floor. And here is the sliding stiffness. So sliding stiffness is calculated basically just by summing up all the stiffnesses of the angle brackets used. And then for the complete wall stiffness calculation, so as I said, so you take a 1 kilonewton force, place it at the top of the shear wall, then you go through the design floor by floor, sum up all the storey drifts, and then you get the total deflection. So I've done that here. So starting with the ground floor, bending moment is 12 because that's the height. Shear force 1. We have a storey drift of 0.34, and then I have done basically the same thing for all of the floors. Summing up here, we have the total deflection of the top of the wall, which is 0.873 millimeters, and then the total wall stiffness is 1 kilonewton divided by that deflection, and we have that stiffness here. So basically, that was the webinar showcasing the new CLT shear wall calculator for designing CLT shear walls in Europe. If you have any questions.
Yeah. Thank you, Philip. That was really great. Yeah, we have actually a few questions in the chat. Maybe we'll have a few more in addition, as Philip mentioned. If you have any additional comments or thoughts, we still have time to cover that. So yeah, we can start with some of the first questions we have here in the chat. So we have one question regarding the diaphragm. So is the design based on the assumption that the floor is a rigid diaphragm?
Yeah. That was I failed to mention that. So the design is we have the assumption that is the CLT diaphragm is rigid, but in reality you would have to in reality is like a semi-rigid diaphragm. So you would have to check the forces when it is flexible diaphragm, semi-rigid, and rigid, and basically do the envelope method, taking the highest forces and then designing the shear walls using the highest forces from those three methods. So if it is flexible, semi-rigid, or rigid.
Yeah, thank you, Philip. We have one more question in terms of connectors. So can we specify more than 2 hold downs?
Connectors? I think currently not, but that will be updated because usually you can place like several hold downs are used next to each other. even though for the connection to the concrete, that is not like a realistic scenario because you're not gaining anything because of the anchors in the concrete.
Yeah, thanks, Phil. Also, just to add that you also showed in the app that there is option that where you can have connectors on both sides. So practically, that's something that is possible. Yeah. And we have additional comments, so that it will be very useful to have this directly link with other FEA softwares as global RFM, like Idea Statica does. Yeah, I think this is great feedback and definitely direction we are also going. Really glad that I see that as a suggestion and feedback for you, but because that's I think in line with what you Philip were explaining at the beginning and the whole process of designing CLT shear walls. So yeah, at this stage we'll have this as a manual process, but definitely we're working on API connectivity with other softwares, and what you mentioned here is something that will probably be working like that. So yeah, not sure if we have any further questions from anyone. Feel free to drop your thoughts or questions in the chat. We have a few more minutes before we wrap it up. Yeah, I think we can finalize the webinar for now. Thank you, Philip, and thank you, everyone. Milica, you want to wrap up the things?
Thank you from my side. If you have any questions at any point, just write us an email, reach out. We are super happy to answer anything. If you have any feedback, always welcoming feedback. Feedback is definitely something that makes us better. So please do send us feedback at any point. And we will announce the next webinar pretty much in the next couple of weeks. So yeah, that's from our team. Thank you all for joining us, and hope to see you all soon again.
Thank you, everyone.
Thank you. Bye.
Bye.
Bye.